All right, we are going to look at the simple harmonic motion system of a mass spring system and how to set up that type of problem. So our goal is we want to get into a format of acceleration of our block on our spring is equal to negative omega squared, which is our angular frequency, times x. If you're wondering why am I trying to get this equation, there is a video link down below in the description that talks about just the general setup of a simple harmonic motion problem and why you want that format and what we can do with it. Okay. There's also a link down below on how, once we kind of figure this stuff out here, an example problem as well. All right, so this is our goal. We have a spring, and our spring is going to follow Hooke's law here. So our force is proportional to our displacement. This is Hooke's law. This negative sign is just telling me that the force is opposite the displacement. So if I push this block this way, the spring wants to restore it back to that equilibrium position. And if I release this mass, it's going to go ahead and it's going to bounce back and forth, oscillating on either side of that equilibrium position at x equals 0. Okay. So here we go. Let's set this up. So the first thing we're going to do is we're going to go ahead and sum up the forces, and we're going to set it equal to ma because that is going to be accelerating at any place there is a force. The only force acting on it in the x direction here is the elastic force, so negative kx is equal to ma. And I'm getting close to this format I want, so I'm going to go ahead and move this m over. And so I get my acceleration is equal to negative k over m times x. So k over m, I got this mirror thing going on, so I have omega squared goes and fits where k over m is, so I can say that omega squared is equal to k, the spring constant, divided by m, the mass. And I can go ahead and find omega then. So omega is going to be the square root of k over m. Using the relationship that the period is equal to 2 pi divided by omega, I can find the period for my mass spring system as 2 pi times the square root of k over m. And so this is my equation. Now, one of the neat things to note here is if I bring my mass further back, I compress it even more, I store more energy in that spring, it doesn't change the period. The only thing that changes the period is the spring constant and the mass. And so what happens is if I push it back further, I get a larger acceleration with that larger x, meaning it's going to be going faster when it crosses this point. So it just moves faster than it did if I didn't compress it as much. So it ends up with the same period regardless of your initial displacement. A cool little thing there. If you're interested in watching the video on an example problem with this, go ahead and go down and click on that video linked in the description.